Hello scientists, thanks for tuning in. This video is about scientific notation. On this slide, I have a comparison of standard notation and scientific notation. The left is standard notation, which is just your everyday typical way that we write numbers. This is like 74, 643, 9,100, and 0.0054. On the right, we have scientific notation, which are the exact same numbers as the ones on the left, but they are written very differently. If you'll notice, they each start with a decimal that is between 1 and 10, and then that decimal is multiplied by some power of 10. So why do we use scientific notation in science? Why can't we just write out the whole number in standard notation every time? Well, the reason why is because it can be very useful with very, very large numbers and very, very small numbers. For example, this number right here is 59 with a lot of zeros, and it can be hard to work with. If you need to use that number in a calculation, you can't even put that many digits into most calculators, and if you did, you might make a mistake and put in the wrong number of zeros. As another example, this decimal is a very, very tiny number that also has a lot of zeros and can be very hard to work with. So instead, we can write these numbers in scientific notation so that they are easier to work with, write down, and plug into a calculator. First, let me explain what the powers of 10 are. When we write numbers in scientific notation, you'll see some number multiplied by 10, and then there is a smaller number in the upper right of the 10. We call those powers of 10. Let's start with 10 to the first power, or 10 to the power of 1. It looks like this. When you have the superscript 1, that means you're taking the number to the first power, and you just have one of that number. So 10 to the first power is actually just 10. Next, we have 10 to the power of 2, or 10 to the second power, or what we often call 10 squared. When a number is to the second power, that means you are multiplying two of them together. So 10 squared is 10 times 10, which is 100. Next, we have 10 to the power of 3, or 10 to the third power, or 10 cubed. When a number is to the third power, that means you are multiplying 3 tens together. So 10 cubed is 10 times 10 times 10, which is 1,000. Then we have 10 to the power of 4, or 10 to the fourth power. When a number is to the fourth power, that means you are multiplying 4 of them together. So 10 to the fourth power is 10 times 10 times 10 times 10, which is 10,000. Next, we're going to have to do 10 to the power of 5, or 10 to the fifth power. What do you think that number is going to look like? If you guessed 10 multiplied by itself 5 times, you would be right. So it would be 10 times 10 times 10 times 10 times 10, which would be 100,000. I'm going to stop here since you probably have the right idea by now. One quick trick I want you to notice though is that when we have the number to the certain power, like for example right here, 10 to the fifth, that's how many zeros are going to come after the 1. So when we have 10 to the fifth power, we're going to see 1 followed by 5 zeros. So let's start off with some scientific notation practice, nice and simple. We'll start with the number 200, which we really don't need to put in scientific notation because it is pretty small, but we're going to do it just as practice. We'll need to rewrite 200 as a number that is between 1 and 10, and then multiply it by the correct powers of 10. One important thing to know is at the end of every whole number, there is an invisible decimal at the end. To create our number between 1 and 10, we have to move that decimal over to the left a few times. If we move it to the left one space, the new number that we get is 20.0, or just 20. Is 20 between 1 and 10? No, it's too big. We need to move it over one more time. So here we have 2.00, or just 2. Is 2 between 1 and 10? Yes. So this is the spot we need to be in. We moved this decimal to the left 2 spaces. This number is important because it tells us which power of 10 we need to use to write our scientific notation. So when we're writing out the scientific notation, we put our new decimal, which is 2.00, and multiply it by 10 to the power of the number of spaces we moved our decimal, which in this case is 2. So our scientific notation is 2.00 times 10 to the second power, or 10 squared. Now, the whole point of writing these numbers in scientific notation is to get rid of all those zeros that we don't need to save space. And we know that 2.00 is the same thing as 2. So we can just write it as 2 times 10 to the second power. Now, how can we be sure that this is the same thing as 200? Well, let's take our 2 times 10 to the second power and work it out. So we know that 10 squared is the same thing as 10 times 10. So 2 times 10 squared can also be written as 2 times 10 times 10. And we know that 10 times 10 is 100. So we could just write it as 2 times 100. What's 2 times 100? Well, it's 200. And that's what we originally started with. So we know that we did this correctly. 200 can be written in scientific notation as 2 times 10 to the second power, or 2 times 10 squared. Let's do another one, 5,300. We need to write 5,300 as a number that is between 1 and 10, and then multiply it by the correct powers of 10. We have to remember that there is an invisible decimal at the end. To create our number between 1 and 10, we have to move that decimal over to the left a few times. If we move it to the left one space, the new number that we get is 530.0. Is 530 between 1 and 10? No, it's too big. We need to move it over some more. So here we have 53.00, which is just 53. Is 53 between 1 and 10? No, we got to move it again. So here we have 5.300, or just 5.3. Is 5.3 between 1 and 10? Yes, 5.3 is slightly over 5, about 5 1/3. So this is the spot we need to be in. We moved this decimal to the left 3 spaces. This number is important because it tells us which power of 10 we need to use to write out scientific notation. So when we are writing out the scientific notation, we put our new decimal, which is 5.300, and multiply it by 10 to the power of the number of spaces we moved it, which in this case is 3. So our scientific notation is 5.300 times 10 to the third power, or 10 cubed. Now remember, the whole point of writing it is to get rid of all those zeros that we don't need. And we know that 5.300 is the same thing as 5.3. So the better way to write it is simply 5.3 times 10 to the third. Now, how can we be sure that this is the same thing as 5,300? So let's take it and work it out. We'll do that multiplication. So we know that 10 cubed is the same thing as 10 times 10 times 10. So 5.3 times 10 cubed can also be written as 5.3 times 10 times 10 times 10. And we know that 10 times 10 times 10 is 1,000. So we can easily rewrite it as 5.3 times 1,000. What is 5.3 times 1,000? It is 5,300. And that's what we originally started with. So we know that we did this correctly. 5,300 can be rewritten in scientific notation as 5.3 times 10 cubed, or 10 to the third power. Let's go through another one a bit faster. 749,000. We need to rewrite it as a number that is between 1 and 10, and then multiply it by the correct powers of 10. Again, we have to remember that there is an invisible decimal at the end. To create our number between 1 and 10, we have to move that decimal over to the left a few times. Once, twice, 3 times, 4 times, and 5 times. The number we end up with is 7.49000, or just 7.49. We can ignore the zeros at the end. This number is about 7.5, which is between 1 and 10. So this is the spot that we need to be in. We moved this decimal to the left 5 spaces. Again, this number is important because it tells us which power of 10 we need to use when we write out the scientific notation. So when we are writing out the scientific notation, we put our new decimal, which is 7.49000, and multiply it by 10 to the power of the number of spaces we moved the decimal, which in this case is 5. So our scientific notation is 7.49000 times 10 to the 5th. But again, we don't need those extra zeros, so we're going to get rid of them, and we say it's 7.49 times 10 to the 5th. If you plug that into your calculator and work the whole thing out, it will be equal to 749,000. Next, let's try one practice problem where the number is actually a very tiny number, a decimal that is just larger than 0. The number is 0.0012. Our goal is still the same. We start by forming a decimal that is between 1 and 10, and then multiplying by a power of 10 based on the number of spaces we need to move the decimal. With this example, the decimal is already there. We aren't looking for an invisible one. But this time, we have to move the decimal to the right instead of the left. One space to the right makes 00.012. Not large enough yet, so let's move it again. 000.12. Almost there, but not quite. 0001.2. There we go. This gives us 1.2, since the zeros in the front don't mean anything. This is the spot we want, since 1.2 is in between 1 and 10. We move the decimal to the right 3 spaces, and that 3 tells us the power of 10 we are multiplying by. However, instead of a positive 3, it's actually a negative 3 because we moved our decimal in the other direction. This may not truly make sense until later years of math, but when you're multiplying a number by 10 to the negative power, you're actually multiplying it by 1/10 a few times. So for example, 10 to the negative first power is the same thing as 1/10. 10 to the negative second power is the same thing as 1/10 times 1/10, which is the same thing as 1/100th. 10 to the negative third power is the same thing as 1/10 times 1/10 times 1/10, which is the same thing as 1/1000th. And when you're multiplying a number by a small fraction like that, you are making it much smaller. So back to our original problem, we figured out that 0.0012 can be written as 0001.2 times 10 to the negative third. And we can get rid of those zeros at the front and just write it as 1.2 times 10 to the negative third.